All right, we're going to talk about the polar form of complex numbers. So we're going to take a complex number and convert it as into a polar coordinate. Remember, a complex number is represented by z, and in this case, we're going to talk about x and y instead of a and b, but the concepts are the same. We can represent a polar or a complex number by x plus y I. So my coordinate plane is the imaginary plane. I have reals on the positive x-axis and imaginaries on the y-axis. Doing this again, just like we did with the x and y before, I can have a point xy, just happens to be in the imaginary plane now, and from that I can also have an angle and a radius. So just like we represent Cartesian points in the Cartesian plane, we can also represent complex numbers using the radius and the angle. And what's going to happen is that it's going to be much easier to multiply and raise complex numbers to a power when we put them in polar form. So to do that, recall that my x values are going to be r cosine of theta, and my y values, which is, this part is the imaginary part, that's r sine of theta. So an imaginary number can be represented in polar coordinates like this. My z value is going to be, the real part will be r cosine of theta. The imaginary part is going to be r sine of theta. But to tell that it's imaginary, again, just like up here, I have x plus yi, I still have the I here, and the y part is going to be r sine of theta. So I just replace the x and the y with r cosine of theta and r sine of theta. Now, since both of these terms have an r in it, a more efficient way to represent this is to factor the r out. So z is equal to r, and then we have the cosine of theta plus I times the sine of theta. That's the standard way to represent an imaginary number using polar coordinates. Now we have fancy names for the radius and angle when we talk about polar coordinates. R is called the modulus. And that's the absolute value of the complex number. So let me show you that. We also say that it is the magnitude of complex number z. So that's what this looks like. R is equal to the magnitude of z, which means it's always going to be positive, or at least the way we represent it here is positive, and that's the square root of a squared plus b squared, using our standard letters for imaginary numbers. So the a part is the real coefficient, b is the imaginary coefficient. Notice we don't have the I in here. It's just the real number and the imaginary coefficient. Now, theta is called the argument. Okay, and that represents, well, the direction, the overall angle of the complex number. So if my complex number is represented by a plus bi in rectangular form, then to get the angle, it's the same as with polar coordinates. Theta is going to be the inverse tangent. This time it's going to be the imaginary part over the real part, and you don't put the I in there, just the imaginary coefficient over the real coefficient. And we always have to remember, we've got to watch our quadrants, because your calculator will only give you first and fourth quadrant answers. So we have to make sure our angle represents the correct quadrant. All right, so we're going to sketch a graph of a complex number and then express it in polar form. So my first example is going to be z is equal to 1 plus I. Remember, this is the complex plane now, so we have the real part and the imaginary part. What this says is I'm 1 unit to the positive real and 1 unit on the positive imaginary, so my point is right there. And what we want to do is convert that. We want to find the modulus, and we want to find the argument. So the modulus, r, is going to be the square root of those two coefficients, 1 squared plus 1 squared. The modulus ends up being radical 2. The argument, theta, is going to be the inverse tangent. Now, you could possibly just look at this, and you know that since they're both 1 and they're both positive, theta is going to be 45 degrees. But if you weren't sure, you would put it in here, the inverse tangent of 1 over 1. Notice we don't put the I in there, and your calculator is going to spit out 45 degrees, which is pi over 4. So if I'm writing this in polar form, 1 plus I ends up being, my modulus is radical 2, and then in parentheses I have the cosine of pi over 4 plus I times the sine of pi over 4. That's how you represent that this complex number in polar form. You have the modulus and you have the argument. And believe me, it's going to be a lot easier to multiply and divide when we have the modulus and the argument. All right, we'll try a second one here. I have z is equal to negative 1 plus I radical 3. And what you'll see in a lot of these examples, your angles are going to be, your sides are going to be similar to the special triangles. You're going to get your special angles out of this. So let's graph this first of all. Here's my real, here's my imaginary. I am negative 1 on the real plane and up radical 3 on the imaginary plane, so my point's up here. So this is a second quadrant angle. Here's my modulus. Here's what my angle's going to be. So we have to be careful with the second quadrant angle because cosine should be negative. All right, so we find our modulus. R is going to be the square root of negative 1 squared. Make sure when you square negative 1, it ends up being positive, plus radical 3 squared. Or if you can recognize a special triangle, you can figure out that you're going to get 2 for an answer. My modulus ends up being 2, because this is a 2, 1 radical 3. All right, my angle is going to be the inverse tangent, but then we have to be careful. The inverse tangent of radical 3 over negative 1, that's going to give you a fourth quadrant angle. You're going to get negative 60 out of that. So what you have to do is you have to add 180 to it to make sure you're in the correct quadrant. I've got to add 180 degrees. So my real argument is going to be 120. And we always write these in radian form. So you got to make sure you have the correct argument. That looks terrible. My final answer then, z is going to be the modulus times the cosine, this is 2 pi over 3, plus I times the sine of 2 pi over 3. If you were to multiply this out again, because you have the correct second quadrant angle, this would turn into the negative 1 that you see in the beginning. So we're going to try some more of these examples in class. The biggest thing being when you converge, you have to be careful with your quadrant sign. But now we're going to finish up by going the other way and taking a complex number in polar form and turning it back into rectangular form. Okay, so this is pretty easy. When you want to convert from polar back to rectangular, all you have to do is distribute the modulus and simplify everything. Evaluate the cosine and the sine, and then simplify it. So here's an example. We have z is going to be equal to 3 times the cosine of pi over 4. So you're going to evaluate your exact values for sine and cosine and the sine of pi over 4. Well, I'm going to do that first. I'm going to take care of the sine of pi over 4 and the cosine of pi over 4. And then I'm going to distribute the 3. So this is 3 times the cosine of pi over 4 is radical 2 over 2. The sine of pi over 4 is radical 2 over 2. And now I just distribute my 3, and I'm back to rectangular form. 3 radical 2 over 2 plus I times 3 radical 2 over 2. So that's how you go back the other way. It's a bit easier than going to polar form. So we will look at all this again in class.